maybe not so bad, but okay, thank you. Thank you very much, and thank you very much for the invitation. It's a pleasure to be here. So, the talk is going to be about toroidal trapped surfaces, and I will in particular try to show examples of such trapped surfaces, both analytical and numerical. And the results that I want to present are obtained jointly with Janusz Karkowski and Edward Malec from Kraków, and with Neil Omurahu from Kok in Ireland, and Naching Si from Fudan, Shanghai. Naching or Neil? Murahu. Yeah. Neil Omurahu, yeah. Well, Neil insists very strongly that his name is pronounced Omurahu, so I will stick to that.
Spelling is probably unfortunate.
Has origin in this. From where in Ireland?
Kok. Okay.
But so you're retired kind of person. We wrongly scheduled your talk. It should be one last week.
Sure, but we discussed that already in the beginning.
But that was done for purpose, otherwise you would have to bring a barrel of Guinness.
Oh, that's true. That's true. Okay. As a matter of fact, well, the study of those examples of toroidal trapped surface, this was not the main motivation of the research that we are doing. So it might be quite surprising, but the primary motivation was focused, well, on estimates of the angular momentum in rotating systems. And in particular, we were working on systems that consist of a black hole and a self-gravitating torus or disk of fluid rotating around a black hole. Now it turns out that to give a proper and well-working estimate on the angular momentum, a relation between the angular momentum and the size of the configuration and the mass in such a case is not trivial, and it's sort of work in progress. And especially we wanted to test the criteria and the estimates that were given quite recently by Khoury and by Naching Si. And it turns out that such results on angular momentum are obtained jointly together with some criteria on the formation of trapped surfaces. So this all started with the aim of testing those criteria of the formation of trapped surfaces, which are not, well, the most trivial trapped surfaces you could think of, but those are really toroidal, as you will see in a moment. Exactly. But that was the motivation. Now the system we are investigating here is slightly different, and I will much simpler, and I will describe it in a minute. The main point is that we were quite surprised by the existence of those surfaces in this case, and I think it's a nice example worth showing here. But because I was told that the audience is not consisting only of experts in GR, I thought that, sure, but I thought that a small introduction to trapped surfaces in GR would be in order here. And it should be also in order because of myself. I'm not working normally in this theory of trapped surfaces, so I was quite happy to have a reason to recall some basic information on trapped surfaces. So When preparing this talk, I was searching for a reasonable introduction, and I found a particularly nice paper by Piotr Hruściel, by Galloway and Polak from 2010. I think it gives some modern flavor of the language that mathematicians use with respect to trapped surfaces right now. Of course, you can start with Hawking and Ellis, the classic book, and most of the information, maybe with slightly different terminology, is present already there. So we start with considering a codimension 2 space-like submanifold of a given space-time. Let's call it sigma. Actually, we should add some assumptions on the orientation, so that basically the difference between the dimension of the manifold
Exactly the same.
in 4 dimensions, it's exactly a 2-dimensional surface. Yeah, sure.
No, it could be not necessarily a space-like surface, I understand. The next assumption is exactly about space-like.
Yeah. In this case, I want sigma to be a space-like.
It will be a space-like.
Yeah, in this case here, yes. Okay. Now,
so we can just visualize this as a surface.
Exactly. Talking about codimension is sometimes more convenient than just talking about the dimension, but you could equally translate that to a dimension. Maybe the case is not so simple if you go to infinite dimensional spaces, but in finite dimensional manifolds it's just trivial. That's just the difference between the dimensions. Now, then, as we will see, there are 2 families of future-directed null geodesics that originate on sigma and that are issued orthogonally from sigma.
So
and basically,
on the surface there are lamps that are shining.
Exactly. And then you have to compute the null expansion of such a family of null geodesics. We will just see in a minute what that is. And if this null expansion is precisely 0, you call the surface sigma a marginally outer trapped surface, or for short, an apparent horizon.
And how does it look when we want to visualize this?
In the simplest case, I think it is in the simplest stationary case, this is just the horizon of the black hole.
That's true. I will come to that point.
In dynamical case, this becomes more complicated.
That's exactly.
It's just a spherical
What exactly is this expansion?
I'm just going to describe that exactly. This is just an introduction, because I always think that when someone wants to introduce a lot of terms and definitions, it's good to understand what's the aim, so the point we want to reach. So basically we will now in a few minutes want to reach a point when we understand, well, the terms in that definition.
One can say that it's time derivative of the infinite area.
Yeah. So, okay. Let's start with the expansion of what's called a null hypersurface. So imagine we've got a space-time with dimension n+1, and in order for all those definitions to make sense, n must be at least 2. N being 3 is absolutely perfect, yes. And all my examples will consider will apply to the standard 4-dimensional. So a smooth null hypersurface in M is a smooth codimension 1 submanifold. Let's call it N, such that if you take the metric and restrict that metric to the tangent space to that submanifold N, then it's degenerate for all P's. So the simplest example one could think of is, of course, the cones in Minkowski spacetime, right? So if you take well, past and then future light cones in Minkowski spacetime, then away from the vertex, they satisfy this definition, right? If you restrict the metric to the tangent space to a light cone, is degenerate. Now, it follows from the assumption on the signature of the Lorentzian metric that there will be a unique direction of degeneracy in each tangent space to that null hypersurface, and it will correspond to some smooth future directed null vector field, which we'll call K right now. It's also worth to notice that the integral curves of K are null geodesics. So this is very simple right now. And we want now to define the expansion of such a null hypersurface. So this can be done as follows. We take capital pi to be a codimension 1 subspace of this space which is tangent to the null hypersurface, and which is transverse to this vector K. So you forget about this direction in which the metric is degenerate, and then the restriction G to the pi is just positive defined. So let E's from 1 to n minus 1 form the basis in pi, which is orthonormal, and then the definition of the expansion scalar for this null hypersurface is just that.
So how does it work for the light cone?
Well, for the light cone, it works more or less as we see it here. This theta is just positive in the future light cone, and it's negative in the past light cone. So basically,
what is the value of theta for the ordinary light?
the very value of that depends on how you parameterize K.
So it's not a geometric.
The sign is invariant. The sign is invariant, and this follows from this very simple scaling property that if you
There is no possibility to normalize the null vector.
K is a null vector, right? So basically you multiply it by any constant. It's still a good null vector, and this is reflected in the scaling behavior of theta. So basically, if theta is positive,
Are there cases where theta gets more information than just the sign?
well, no.
Okay, look, there is a possibility to squeeze out of this some invariant. In any case, this reparameterization of K may be treated as a gauge, as some gauge, and there is a kind of a gauge field which you may feel now.
All right.
Is there a possibility to form a gauge invariant?
Yes.
Counterpart of
Together with
expansion?
other.
So
So it does not carry much information, just the sign.
yeah, but that's what we will be interested
That's
in.
only the sign is.
Whether it's going forward or
Yeah. You could have a similar construction for time-like geodesics, and then you could parameterize time-like geodesics by a affine parameter, and then it's sort of fixed.
There are
But
three possibilities, not just two.
zero.
Plus, minus, or zero.
Zero,
where,
yeah.
Apparent horizon corresponds precisely
zero.
to zero.
okay. So basically, right now we are talking about the two situations. Either your family of null geodesics is divergent, or it converges.
Or is in a case the volume is stationary.
That's right. The area.
There are three possibilities.
Okay. So.
Not in Minkowski.
No, in Minkowski only two, of course. In Minkowski.
So now, actually.
Okay, in Minkowski, if you pick up a null plane, just a plane,
Okay.
then it has zero expansion. Null plane. But of course, it is not compact. Null plane has zero expansion.
It's a surface.
Yeah.
Because geodesics are.
Yeah.
The expansion is just the increase of the distance between.
Not the
Yeah.
distance, just a truth. In any case, this formula for expansion can be replaced by the following. That you take infinitesimal two-dimensional volume and you follow K. And now this volume may either increase or decrease or become stationary.
That's right. Of course, the null plane is also a good example of what's called null hypersurface, but it's a wrong example with respect to this theta, because you do not have the property that's crucial. Now, usually when people write about trapped surfaces, they start with a different setup. They start immediately with a space-like submanifold, sigma, with codimension 2, so in our 4-dimensional case, just a surface. Well, we want to assume that sigma is compact, and all our examples will apply to that case. And then each normal space of sigma, so basically the space that's orthogonal to the tangent space, is time-like. So the restriction of the metric to this space is simply Lorentzian, and because of the dimensionality, it's two-dimensional, and it has two null directions which are orthogonal to sigma. Right. And let's denote them as L plus and minus. These are standard. This is probably right now a standard notation for those directions. Now, if you have this, you can construct the so-called null second forms that are just tensors that are defined by this formula. Right? So you basically take a covariant derivative of this vector L, plus and minus, and you multiply it by another vector field, and you get a tensor which is defined like that. And then if you have it, you can compute a trace, but with respect to the metric that's induced on the surface sigma, and you call those theta plus and minus the two null expansions. Now, it's important to understand that basically what we have here is precisely what we had before, namely if n plus is just the null hypersurface that's generated by null geodesics that pass through sigma with the initial tangent vector lambda L plus pointing to the future, then theta plus is just the null expansion of n plus in this previous sense, and the same applies to when restricted to sigma, and the same applies to L minus and theta minus. Right? So these are basically the same definitions. It's only that right now we specialize to the case when you've got a two-surface which is space-like, and there are two null directions that originate from this space in every point. Now, in mathematical general relativity, it's customary to think of some initial data approach, and then what you consider normally is space-like hypersurface in the space-time mg. Let's call it sigma, with the second fundamental form kij, with some metric that's induced on this, well, in standard case, three-dimensional hypersurface, space-like hypersurface, and let U be a future-directed unit vector that's normal to S, right? Then a surface sigma that we are talking about can be embedded in such a space-like hypersurface. Right? So we just consider this sigma as a standard two-dimensional surface which is embedded in a time slice. Right? And then you could think of the properties of the sigma as properties of the originary surface which is embedded in a three-dimensional time slice. And then let's call an outward pointing vector, which is normal to sigma, and which is a vector in S, simply an n. And then you can see that L plus and L minus are simply U plus n and U minus n, right? So this tells you that if the sigma has, well, two sides, well, let's think of a compact surface. So by convention, for instance of a sphere, so by convention you call one normal vector an outward pointing, the minus n would be inward pointing, right? And then you see that the L plus and L minus, which we're talking about just before, are simply connected with those directions, the outward direction and the inward direction. Now,
the Lorentz transformation acts in such a way that L plus is multiplied by some factor and at the same time L minus
exactly.
Divided by the same factor. So you see
Exactly.
why the length of L cannot be fixed.
Exactly. It's a simple exercise that you can do in 2D in Minkowski spacetime actually to see that. Now, well, in most practical situations, it's good to describe those expansions theta plus minus in this setup, and then it turns out that the theta plus minus are expressed as plus minus h and additional terms that come from well, the extrinsic curvature with that come from the well, the information on how these space-like hypersurface, how time slices are embedded in the space-time. And the h.
The surface of the sphere, what would be theta plus minus if you have a sphere?
That depends on how well, you take a sphere,
Yes.
and then the sphere is embedded in some time slice.
Yes.
And then it depends on how this time slice is embedded in the space-time. Because the propagation of the rays of light depends on the structure of the space-time. So that depends on what happens when you start propagating in time.
So under the Lorentz transformation, this hypersurface hyperbolically rotates, right? The three-dimensional hypersurface.
Yeah.
Under Lorentz transformation. Yes.
Yeah.
And what happens then to theta? What is the difference between two thetas under Lorentz transformation? What happens to theta?
I would would have to think of that.
Because it can be applied to Minkowski.
Of course. I would have to think of that. I just don't want to give a stupid answer right now. Mm-hmm. Now, but of course, if you choose your embedding of your time slice so that Kij is 0, right, which in many cases you can, then all that vanishes, and then theta plus minus is just all components of Kij. Yeah, that's possible. That's possible. Then h, then theta plus minus is simply plus minus h, which is the standard geometric mean curvature of sigma as a surface in S. Right. So then, this covariant derivative has to be computed with respect to the metric in S. Okay.
So in Minkowski space, it's a normal divergence of the N vector.
Well, in this case, yes. In this case, yes.
And the tension in the definition of H, the covariant derivative is a three-dimensional derivative.
Yeah, exactly.
Not
Exactly. This is what I just mentioned, that this covariant derivative is computed with respect to the metric in S.
Three-dimensional.
Exactly. This is three-dimensional. Right. Now, so basically, for round spheres in flat Euclidean slices of Minkowski spacetime, you have theta plus, which is positive, and theta minus, which is negative. Right. So the null geodesics that are emitted outwards are divergent, and those emitted inwards are convergent. And that terminology is that sigma is called a trapped surface if and only if both thetas are negative. Right? Okay. Which is, of course, strange to imagine and probably difficult, but this happens in strongly curved geometries.
Well, at the horizon, this is something which is easy to imagine, right? Because the issue is that the photon sent outwards is just standing, right?
Yeah. Okay, yeah.
And the one sent inside, it's going.
Yeah. Okay. I absolutely agree. Now, okay. It turns out that in many technical cases, it's sufficient to focus only on one of the thetas, and many theorems would work if you only analyze one of the thetas. And by convention, let's choose theta plus, and then there is a special terminology that when theta plus is negative or theta plus is positive, you call sigma an outer trapped or outer untrapped surface, respectively. And this word outer refers to the fact that you only choose one theta, not two of them. And the surface is called a marginally outer trapped surface, or as mods, if theta plus is 0 exactly on the entire surface. Right? So basically that completes that definition. Now, this is a purely geometrical terminology. If the surface has a mean curvature that vanishes, then we say that this surface is a minimal surface. And this is connected with the fact that the condition that the mean curvature vanishes is obtained from the variational principle when you consider the area of the surface. Right? So you take a surface, you consider...
That cannot happen in Minkowski space.
This cannot happen. Well, let me come to this point. Okay.
Similar so field.
Yeah. So these these are minimal surfaces. Now,
The notion of a minimal surface is the same as for this one.
yeah, exactly.
Even catenoid,
Exactly.
helicoid has minimal surfaces.
Yeah, exactly. There is also a frequently used term which usually appears as an abbreviation, CMC, and that stands for constant mean curvature. The situation when h, the mean curvature, is constant along a given surface. But that just comes here to complete the terminology. Now, there is a nice theorem by Penrose, I think, that basically an existence of a trapped surface implies that the space-time is future null geodesically incomplete. There are some technical assumptions. You have to or the space-time has to fulfill the null energy conditions and has to be globally hyperbolic and things like that. But basically, this gives you a feeling that whenever you've got trapped surfaces, that probably signals that there is a black hole. And also it can be shown that in stationary spacetimes, intersections of an event horizon with a space-like hypersurface have theta plus being 0, so that these are marginally outer trapped surfaces. And that's the reason why the notion of apparent horizon became so popular, probably, especially in numerical relativity, as a replacement for, well, probably more proper notion of the event horizon. To understand that you've got an event horizon, you should, in principle, know the entire evolution of the system, namely the entire space-time. And marginally outer trapped surfaces or apparent horizons are just replacements for the horizon that you can define on a given time slice, right? Completely locally by means of the construction that was described here. Now, I mentioned already that mods are, well, in a sense, analogical to minimal surfaces that you can consider in the Riemannian geometry. Probably there is no analog of the area functional, right? So, as was mentioned. But for minimal surfaces in standard geometry, there is a notion of stability, which is as follows. You consider a suitable class of variations of the surface, you deform it. And if the second variation of the area is positive for a given surface, then you say that it's stable, right? The first variation is 0. It's a minimal surface, and now if all local deformations increase the area, that means that you really have a minimum, and that's referred to as stability.
Minimal surfaces in normal Riemannian geometry can be drawn. Can you draw the mods?
Well,
it's a two-dimensional surface, so in 3 dimensions we have enough.
Well, they can be drawn. The point is whether you notice that these are more marginally outer trapped surfaces, right?
So in the case of
I will draw them in.
in the case of curve metric, you can change the area of the horizon, right? So I'm a bit confused because when you extract rotation from the black hole, your horizon shrinks.
No, the point is.
There's
No.
something
You
irrelevant.
slightly change the initial conditions. And you see what happens with this area.
So it's against the local thing and not global slow evolution.
No, but
Because there are curve metrics with different areas. The problem is when you're having
Yeah, but okay. So, because there is no area characterization of mods. There is such for minimal surfaces. Then, well, there is some kind of replacement for the idea of stability that might be of interest. Actually, I think it comes from well, at least two papers by Anderson, by Mach, and by Simon. The idea is to construct a certain operator that would reflect the way in which a variation of the surface acts, and then it turns out that it has principal eigenvalue, the one with the smallest real part, which is completely real, and then there is a condition that you can introduce saying that the mods is stable if this smallest eigenvalue is positive, and in the case of minimal surfaces that reduces to the standard definition in terms of the area. Now, whether anyone is satisfied with that definition, that's up to the scientist.
Stability means that it does not decay in time, or when it's stable. So, what is the sense of stability? Here we have space-time, right?
Yep.
Space-time evolves according to. Do we consider the Einstein spaces that have the?
Well, I will not say that I have a good picture of this stability here. So let's. I would like to call it like that at the moment. Just not to provoke any wrong.
Right? So you can
No, it's not simple.
so you cannot untrap everything or
Well, it works in a sense that in terms of this definition, you can show that the outermost marginally outer trapped surfaces, those that do not have any other that are not contained in any other trapped surface, that they are stable. So that works in that sense. Okay, so if
Does it have much to do with normal notion of stability? Okay.
I would say so. Yeah.
I would say it this way: if this operator in general has got a zero eigenvalue, this means that you can somehow deform this marginally outer trapped surface and still retain the marginally outer trapped surface. So if this condition satisfies that the surface is in a way locally unique, you cannot deform it.
Yeah.
It's a unique surface, which is
Okay. I buy it. Okay, so let's come to the main topic right now. So I promised nice non-trivial examples of mods that are tori, and that is constructed for a solution that was introduced by Nilo Murahu already in 1986. And that is actually an extremely simple solution. You just take initial. Let me describe it. These are the initial data for Einstein equations that are momentarily static. So you assume that Kij is precisely zero everywhere, and that are given by a free metric, which is written explicitly here in conformally flat form. So there is a conformal factor that multiplies the flat metric written in spherical coordinates here. And you choose this conformal factor in that way. So up to some radius R0, you choose that function, and up above that radius R0, you choose a different one. And then,
fluid is how many times differential?
one for sure.
One.
One for sure.
But one is not much. Is it twice differential?
I doubt. No. 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 It's just once. Not
Yeah,
really.
of course, but,
Not really. It doesn't introduce any mass in. It doesn't introduce any mass in the energy momentum tensor. No. So
for
that you.
instance, the
Well,
Christoffel symbols are not continuous, yeah? Or they are?
Well,
No, they are. They are continuous, but
yeah.
but the curvature is not continuous.
Yeah, exactly. And this is what you see here, right? So if you consider, if you compute the Ricci scalar, right? The three-dimensional Ricci scalar. Obviously discontinuous is a constant here, and it's zero outside.
Isometric to a SV sphere glued together with the Schwarzschild, right?
Yeah.
This is a
Yeah. So this is very, you could understand this as a slice of Schwarzschild outside R0, right? That would be a slice of Schwarzschild, and glued to a piece which has constant Ricci scalar. And if you plug that to the Hamiltonian constraint, to one of the Einstein equations, you can, well, which has that form, you understand that because Kij is 0, that means that the energy density is simply constant within the sphere of the radius R0. Right? So this could be understood as the initial data for a star of constant density. Of course, in order to say that this could be a star, you would have to define what happens when you switch on time, right? But at the level of initial data, you could say that this is a star of constant density. Now, as you see, there is a three-parameter beta here, and it turns out that if depending on the values of beta, you could have horizon outside of R0, which would be a standard Schwarzschild horizon. So, well, the beta would be related with the mass, standard Schwarzschild mass of the space and R0 as that. And if you want the immediate application of the definitions of mods that I've given, then you could start searching for spherically symmetric, simply for spheres that would be marginally outer trapped surfaces, and it turns out that there are such. There are spheres with h being 0. They are also minimal. So basically, if we are talking about mods here, we could also equally well talk about minimal surfaces because Kij is 0. So the only characterization is in terms of the mean curvature. So if you do this, you see that there is such a sphere at R being m over 2 exactly, which is precisely the location of the Schwarzschild horizon, but simply note that we are working in the coordinates that are conformally flat here. So this is a standard Schwarzschild horizon. But also inside the star you could find a minimal sphere at the radius r being 1 over square root of beta. And if you consider the area of those spheres, right, you would see that the one outside has actually is a local minimum of the area. So this is actually a stable minimal surface. It's an outermost horizon, so to speak. But the one at r being 1 over square root of beta is actually a local maximum of the area of the sphere. Right? So it's a minimal surface in a sense that it has a vanishing mean curvature. It's a MOTS, but it's unstable in the sense that was described before. Now, but I promised toroidal spaces, and that's where nice things start to happen. Yeah, I know, but
10 minutes left.
yeah, I think I manage. I think I manage. So this is done in toroidal coordinates. You could actually describe those tori also in standard cylindrical coordinates if you don't like toroidal coordinates, but actually the discovery was made in toroidal coordinates. These are the standard relations between toroidal coordinates sigma, tau, and phi with the Cartesian coordinates. Probably the only unusual thing concerning toroidal coordinates in this setup is that, tau is a quantity that sort of plays the role of the radius, the distance from the circle on the equatorial plane, but it's measured in the reverse order. So tau being infinity corresponds precisely to the circle in the equatorial plane of the radius c, right? And tau being 0 is infinity. You can express the metric in those coordinates. There is nothing extraordinary with that. And you can also consider a toroidal surface that's parametrized as follows. You simply say that tau is any function of sigma. And then, quite generally, you can write the expression for the mean curvature in those coordinates. And it's complex, and it's even more complex than you see here because those conformal factors enter here. Right? So now let's take the conformal factor as corresponding to the inside of the star. And the task is to solve that, to search for special cases here. Actually, we were interested in vanishing age, and it turns out that you can have special cases, because quite miraculously, if you just consider a coordinate torus, so you say that t is simply constant, and if you restrict yourself to the inside of the star, and if you choose appropriately this coordinate, this radius c, that only defines the coordinate system here, then it turns out that h is given by that expression, which is a constant. It doesn't depend on sigma, it doesn't depend on phi, it only depends on tau. Right? So this gives you a whole family of constant mean curvature tori in that star.
Excuse me, I'm quite confused about the geometry. So
It's spherical.
The star and
No, I didn't.
Or you have
No, I didn't. No, I didn't. It is a star.
This inside
Exactly. That's why I think it's nice to understand that.
Inside, yeah.
Exactly.
Inside, so
You've got a star.
it exists also for a Schwarzschild.
No.
Because it's inside this.
No.
There is this constant density of energy.
Exactly. This doesn't have to be a static space-time, right? That depends on how that would evolve. But so this is a spherically symmetric space-time, but I'm not forbidden to search for toroidal surfaces. Exactly. So this is a spherically symmetric spacetime. The star is spherically symmetric. I just ask for the properties of toroidal surfaces inside the star. So of course, because of spherical symmetry, if I find anything interesting here, I can rotate the axis of the coordinate system, and I find the same. But still they are. And these are actually not only toroidal, these are exact coordinate tori in those coordinates, and they are given, well, as you see here, and h is just given by that expression, and if you choose tau being precisely that number, then h is 0, and this is a marginally outer trapped surface. So these are examples that show you how they look like.
Does that mean that inside of a star you have something like a family of donuts?
Exactly.
So you fill up a sphere with donuts?
Exactly. Precisely. Yeah, that's...
Any orientation.
With any orientation. With any orientation. That's exactly how that works. So actually in this picture, these are just circles, or parts of the circles.
And those donuts, they cannot intersect, right?
They cannot intersect. And they don't.
So what happens inside?
No, they can, because if the rotation...
Well, if you rotate, but if you rotate, of course, yes.
One fixed
Okay.
toroidal coordinate system,
Okay.
they do not.
Okay. So this just shows you how that depends on beta. And if your beta
What
gets...
does that mean physically?
Let's come to that in a moment.
We are so
Yeah.
I understand something physically.
Okay. And so this is just... Okay. This is... Well, these are just story. And if you take beta, which is small enough, then it turns out that the mods, those minimal surfaces will also exist, but part of those surfaces will exist outside of the star, and these are no longer tori, but still they are toroidal, and basically this picture shows you how they depend on beta. So basically, with decreasing beta, they sort of glue to the surface of the star, which is set at 1, being 1 here. Now,
And if beta goes well below 1, or it goes to 0,
no.
when
So the point is
they are
that
going back to the Schwarzschild, what happened to those?
they do not exist. They stop to exist. They only exist above beta equal 1, and they always exist beneath the horizon, which is spherical. Which is the outer horizon is dictated by symmetry, so to speak. Now the thing that I find intriguing here is that you see this foliation by tori of constant h is entirely dictated by the properties of this coordinate system. And actually, I've taken this picture from Wikipedia. It's from the article on Apollonian circles, and the surfaces, the surfaces of constant tau and sigma are just families of circles, and they are Apollonian circles. These are circles that, well, every circle from one family crosses every circle from the second family in 2 points, and they cross always orthogonally. And to be honest, I cannot find any explanation why this quite sophisticated solution of initial data for GR with this star would give you the structure of CMC surfaces, and the minimal surfaces with one of those blue circles would correspond to the minimal surface, and the mod that exactly coincides with this well-known diagram for toroidal coordinates. That's what I don't understand right now. Now, this is the final part. Those tori also have strange geometrical properties. Probably there is no physics in that, but let me mention this maybe very briefly, probably on the blackboard. Let's consider such a torus of constant h that we have just constructed. You could imagine you have, well, an outer circumference here, the cross-section of this torus with the equatorial plane, so you take the outer one, and you take the inner one. It turns out that when you compute the circumferences of those circles, they are equal. But it's also quite surprising that for the case with h being 0, okay. Yeah. But that's just a strange coincidence of well, this system, and this of course comes from the fact that it's really strongly curved. But if you consider the torus with h equals 0 and you take the circle which is just a meridional cross-section of this torus, that circle, it also has the circumference that is equal to the well, the two remaining ones. So, you know, you cut that torus in different ways and you get the same circumference. This is not the largest circumference. The largest is contained within the torus. It lies on the equatorial plane. It's precisely in r being 1 of the square root of beta. It's precisely where this spherical minimal surface exists as well. Now, and this is the last important slide that where I want to mention the tests.
Give a special equation of state for the. I mean, the star is after all made out of some matter.
There is no. You would have to consider an equation of state if you start thinking about the evolution.
There is a right-hand side of it.
Yes, it's constant row inside.
Yeah.
It's just initial data. We don't have
Initial data.
Exactly.
If you run time evolution,
Then you would have to.
This probably has an analytical time.
But this initial data, I mean, this which leads to all this fantastic mathematics which I just admire and have no slightest.
I see how you
follow. I mean, what does it mean physical? I mean,
Basically means that
I mean,
you set up initial data.
yeah, but this
The
initial data correspond to what?
Star with constant
Yeah.
density of radius r.
Okay.
And those equations of state may be very different. At this moment, they don't count. Of course, if you want
That's
to
right.
have in mind a specific physical model, you have to precise the equation of state and so on.
Yeah, but
Okay.
I have this geometry that I should have been able to calculate it. How
No,
density-
no, no.
In order to solve the
I can solve the Einstein.
Now, if you
No.
the Einstein equation have to be implemented by
Nie.
state equation. by equation.
Nie. Wszystko jest.
But I have the matter. But whatever is set here, I have a real intensity
Nie.
that corresponds to this tremendous strange thing. Never mind how
Nie.
I calculated.
W danych początkowych nie ma nic o ciśnieniu.
Yeah, it's
W równaniach więzów nie ma ciśnienia.
Then I can suppose I write the right-hand side of the
Okay,
equation, that
well-
this is just a fluid
Yeah.
with the density and pressure as simple as possible. Can I solve that? Is this consistent with this?
Yes, it is. For it is consistent. Of course, you cannot solve them analytically.
I
Probably.
don't care whether I can really solve it. This much I can understand. The question is,
You can. You can.
what happens with this matter?
It depends upon the equation.
The equation of state.
The equation of state.
Again, I just define. I said, I mean, it's just a simple fluid, the ideal fluid, and I put the right-hand side of your complicated
You still have.
tensor, I put, or an Einstein tensor, I put the energy momentum tensor corresponding
Yeah.
to the simple
Okay.
fluid.
So this is absolutely compatible with perfect fluid.
And then I
You
ask
have to
what
specify
happens
the
to this
pressure.
Fluid, how that is possible.
Sorry.
to reconcile this
Let's-
particular contraption with the density of state.
You have you.
But I
If
just
the fluid doesn't know anything about these constructions.
yeah, but I have a star which is made out of that fluid.
Okay.
And inside I have this funny core.
No, you don't
No,
have this
no.
inside. The star is just a round
Exactly.
object with constant density.
Exactly.
Does not know anything about these round surfaces.
Precisely like that.
So what do they do
Precisely
with
like that.
surfaces?
The surfaces are interesting mathematical
Exactly.
concepts.
will somehow change in time.
Exactly. And my lesson from that.
And if you have
The metric. This is
sufficient,
the
Okay. So my
you have sufficient amount of money to invest, then people may try to answer
Okay.
your question.
I would invest it in another way.
Okay.
Whatever.
Okay.
This one.
Okay, so basically, answering this question, my lesson from that would be that mods inside that kind of systems, although they fulfill all the formal definitions that we are used to and so on, they do not tell you really much about any physical invariant properties. Because as you see, and as was noticed already, thank you very much for that, you can rotate the system and you still get mods, right? So they are not unique in any sense,
They're
right?
not real objects.
And probably the answer from the mathematical point of view is that they are not stable in the sense of those complicated definitions, right? Because they are not. Exactly. But nevertheless, if you only stick to the definitions concerning the propagation of the rays of light and so on, everything's perfectly fine here. And yet you see, they are not unique. They are not what you would expect from the horizon to be. Now there is a technical lesson you can also learn, and that's why that was all investigated. Namely, you can have criteria on the formation of trapped surfaces, and this example is adjusted to the topology that we had in mind, that you could have a toroidal system instead of spherical one. So you could have a criteria for the formation of trapped surfaces with that topology, and actually they are tested and fulfilled, although not quite trivially. So it's another strange coincidence here that if you compute the mass within a torus with h equals 0, well, you compute this properly covariantly with the proper volume element.
Corresponds to
You take this. You take. No, it's this row from the star. You take this row, and you compute how much of this density is contained within the torus, right?
It's a constant row.
It's a constant row.
This row is related to beta.
But the metric.
Exactly. This is just a constant. You can take it out from the integral, right? Then, if you define a sort of circumferential radius that would tell you what's the largest circle you can have in this object, and that's where you see that this is adjusted to the toroidal topology. This is not the aerial radius, it's a circumferential. Then the important point is to understand where this largest circle is, and it's not the outermost circle, it's inside. And so you basically define your radius, the measure of your size of your configuration as the circumference divided by 2 pi. Then it turns out that for all those tori, irrespectively of beta, 2 times the mass in the torus divided by pi times L is always 3/4. Now, the theorem by Curie and Xi gives you basically that it has to be smaller than 1. Right? So it survives. If you do a mistake and if you take the wrong radius here, then you will see that something is wrong here. Right? So basically that's the technical part. That's what you use that for. just to see that in those theorems that are devised especially for this toroidal topology that you could deal with talking about well, tori around black holes, that they are satisfied. But for this, of course, you have to have a nice example of the trapped surface. Now that's the whole thing, right? I still don't.
3/3 quarters correspond to the very specific choice of initial data, and
It's for that, right? So we cannot, you know, improve the theorem, right? In that way, we just show that if everything's all right. Well, I think during the discussion we have mentioned already those points, right? So so let me just stop here. Should I?
Probably. I just would like to make a very short comment regarding the physical meaning of those toroidal surfaces. So we can even consider example of Minkowski space, and it is foliated by toroidal functionally trapped surfaces. So we see that we have to consider those structures more like mathematical structure of the geometry rather than encoding particular physics.
Excuse me, Minkowski?
Yes. In Minkowski, you can build a foliation by essentially non-toroidal horizons of vanishing curvature.
Oh.
Yes.
Well, but some yeah.
Good partners. I think I have a suspicion why there is no dependence on beta in this result. That's my first comment. And the second comment is, it seems to me that your setup should be able to follow like quite a lot about the time development of these things, because I believe you can analytically solve the Einstein equations without the pressure in your initial data. I suspect you can do it.
Well, this would, well, this should collapse. Well, probably we all agree. So this would mean you get the a good analytical solution to the collapse.
Which would be interesting because it would tell you something about how they form these toroidals.
Well, but you are absolutely free to work on that. So.